All right. Good morning, everyone. Hope you had a nice, slightly longer weekend. One of the fun things with being a student is when your quote-unquote work hours is not well defined. So that gets a little tricky. I know days off aren't always days off. But I do hope that you started to look at the problem set, that you started to do some of the problems. If you haven't, I really encourage you to start doing that sooner than later. This is very much one of those things. Get in the good habit of being on top of this early, because it's one of those things that later on, it's hard to develop good habits later on. It's one of those you start really strong, and you accept as the semester goes on, you might, lax up a bit. Doing the opposite is much harder. It's really hard to start lax and get more strict. So stay on top of it, set a rhythm for I want to get this many problems done in this much time, yada yada. I highly recommend that. The first quiz, I think the due date's a little bit extended. Normally they do on Saturdays. I have to double check. Either your first quiz is due this Saturday or next Wednesday. It's on WebCourse, as you can see. But remember that quote-unquote quiz is basically checking. My assumption is by this Saturday you should know those things. By the due date of that quiz, that's the purpose of it, is you should know those things. And the purpose of the quiz then is to check if you know those things. It is not practice. It is not sufficient as practice. 5 questions are not sufficient, hence the problem sets and all that. So, I'm going to do a couple of problems. I'm not going to spend too much time on these. I'm going to kind of whiz through them pretty quickly because I want to get to the next things. However, these problems I will post the full worked out solution to. If I don't have the time to fully write it out today, I will either post the full thing and I may, I'll at least do that. If I do more, I'll let y'all know. So, there's 2 problems we're going to do again. I'm not going to spend a ton of time on them, about 15 minutes or so, because I want to get into electric fields so that we can, stay on pace and things like that. This problem is, let me read the problem and then tell you all what skills that we're going to be working on here. We have 4 particles forming a square. The sizes of the square are A, and each of the charges, the one on the top left is positive Q, the one on the top right is negative 2Q, the one on the bottom left is positive 2Q, and the one on the bottom right is negative Q. And the question is, what is the net electric force on Q1, and in what direction? Now the answer here, direction, is kind of there, kind of sort of. So, this question is as much physics 1 as it is physics 2. You'll see what I mean as I solve this. This problem is a net force problem. And the only thing that's new in it is calculating the forces. That's the only thing that's new. But once we draw the arrows and write the expressions, after that it's just going to be some physics 1 kind of stuff. It's net force equal to blah, blah, blah. So, great. This is going to be a lot of physics 1. The other thing that's unique about this is notice that the answer is purely in variables. This is a trend you're going to see in this class, that there's going to be a subset of problems, not all of them, but a subset where we don't actually plug in any numbers. And believe it or not, in my opinion, these problems are easier. You're going to be like, how are they easier? I'm so used to plugging in numbers. Plugging in numbers is an extra step. In fact, part B literally just says, hey, what if you had the numbers, plug them in? It's an extra step plugging in the numbers. When you build the equation with the variables, that's one less step than having to plug in the numbers. So it's actually less work. Plugging in the numbers means you need a calculator. Plugging in the numbers means it's, you gotta actually do that stuff. So anyway, we're going to see these problems, and I want you all to get used to manipulating in purely variables. You all have probably been used to just plugging in numbers immediately. Working in variables is better. It's better because Q will always mean charge. A will always mean distance. Whereas once you plug in numbers, it's very easy to lose track of what the numbers represent anymore. And so you start doing a bunch of work and you forget what you're even doing work on. It's just a bunch of numbers and they all get confuddled together and it gets really kind of messy. When you work in variables, it's much easier to see what is what and keep track of things, and it's just less space and less work. Physics majors, upper level courses, we just stop using numbers entirely. Every single problem is come up with the expression, come up with the expression, come up with the expression. For engineers, one of the benefits of working with variables is if you're doing 3D modeling, there's something called parametric design, where what you do in parametric design is instead of saying the length of something is 5 millimeters, you say the length of it is A. And then you have a table where you decide what the value of A is, and you can change the value of A, and it'll update the model dynamically. Parametric design is much better to do because it's much easier to update your model, and basically all your measurements are variable, and then you have a data table where those variables match that thing. So there's reasons for doing this. Okay, so first step to every single problem we ever solve is what are we solving for? We are solving for the net electric force on Q1. We are asking what is the force on this charge? The force net on 1. You know, that's the end goal. Okay? Anytime you all see anything asking about what the net force is, you immediately should think of what are the forces acting on it. That should be the next logical question anytime you all see anything with net force. Net means total. Total means sum. Sum means you need to add up things. What am I adding up? In this case, I'm going to have the forces of each of them. So we're going to go, the picture's already here, but we're going to draw some arrows on it. So one thing I'm also going to do, just to make our record keeping a little simpler, this one's Q, this one's 2Q. I don't want to read the problem again, so I'm just going to kind of jot all these down. And then I'm going to go through and write the force of 2 on 1. Each of these charges is affecting charge 1. So we ignore the bottom ones and we say, what does 2 do to 1? Well, they are both positive. Nope, they're not. I missed a negative sign. Good thing I checked. Q1 is positive. Q2 is negative. So therefore, F12 is going to be to the right. How is charge 1 affected by charge 2? And if you want, we can maybe write this a little differently. We could do the force of 2 on 1 if you wanted to, if that's the notation we would use as this force. The force of 2 on 1. Charge 1 is being pulled towards charge 2. Opposites attract like charges repel. Great. Now we're going to do the force of 3 on 1. That's going to repel. We're not super worried about the size of these arrows at this point, but the direction very much matters. And then the last one, the force of 4 on 1, that is going to get attracted. And the reason that's going to get attracted, again, is opposites attract like charges repel. Yay! I got 3 forces, 3 vectors. The next thing I need to do is I guess you can do this in 2 different orders. Pick your poison. I'm going to go ahead and write, remember these are vectors. So I'm going to find the net force on 1 in the x, and I'm going to find the net force on 1 in the y. I'm actually going to build those equations. Remember, net means sum, so this is physics 1 right now. I'm not doing anything physics 2 yet. The only thing we've done physics 2 is the opposites attracting like charges repel. But building this equation, this is physics 1. I got 3 vectors, add them up. So on the x direction, so actually I'm going to write, we're going to do 3,1x plus f2,1x plus f4,1x. Now, there is no x component of 3,1. 3,1 points straight up and down, so it's actually 0. So, I'm just going to get rid of that. I wrote it just to, be a bit methodical here, but 3,1 doesn't have an x component. It points straight up and down. F2,1 points purely in the x direction, so that one's good. F4,1, and notice I'm in more plus, 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 plus. One of the things to be careful of, you look at this left, right. F2,1 points to the right, so it's positive, yay. F4,1 points to the right, so it's positive, yay. One of the things I'm going to do before I move to the next thing, so F2,1x is just F2,1, because it points purely in the positive x direction. I don't need to break it into components. F4,1x, I need to break into components. So to remind you all, here's F4,1. I need to break it into its components. Classic, right? Vectors. Remember that you have to do this. To break it into components, this is a 45-degree angle. How do I know that? You can kind of see that it splits the 90 degree in half. It points directly down to the right. Geometry, geometry, you can figure out that that's 45 degrees. If you're unsure, it's a good problem to think about. So if I want the x component here, f41x is going to equal f41 times cosine of 45 degrees. Not because x is always cosine, it's because the x is adjacent to the angle. Keep that in mind. Do not get in the bad habit that cosine is always x. It is not. In fact, the next problem I'm going to do with you all, it will not be that case. So great. So this is f41 times cosine of 45. Great. Built the equation. We're going to do the same thing down here. So we're going to do f31y plus f21y. And I'm going to make them all plus for now, and I'm going to fix it after. f21 has no y component. Get rid of it. f31y is just f31. It points purely upwards, so that's positive. f41y is going to be minus f41 times sine of 45. Why? Because it's pointed down, it's the y component, you go up to the triangle. Again, this is kind of physics 1 things, but these are the skills you all need. Alright, so we built our expressions, and the last thing that we have to do, I guess there's kind of a couple more steps, but then I'm going to jump to the next problem after this. So I'm going to steal all of this and go to the next slide, just to give myself more space. Pro tip, give yourself space. When you're solving problems, do not try to cram it on a small piece of paper. Take your time, take your space. When you cram it in there, that's when you make mistakes. All right, so the last things we need to do, the major things, is we need to calculate the values of f21, f31, f41. How are we going to do that? Remember that the force between any two charges is k, q1, q2 over r squared. That's the expression for the force between two charges. So now we're just going to do that. We're going to put that in here. So f21 is going to be k. The value of q1 is going to be q. You know what? I'll write this first one like this, and then I'll plug it in. So k, q times, now these are magnitudes. Do not put negative signs in here because it's going to throw everything off. These are magnitudes. We figure out direction from the picture. We get the magnitudes from this equation. So we get q times 2q, and my distance here is a because, there's a. That's the distance between the two charges. So there's that one. F31 is also going to be really straightforward. In fact, it's the exact same thing. Q1 is going to be Q. Q3, here, I'll write it the same way just for helping you all out. So that's going to be K times Q times 2Q over A squared, because the distance between 1 and 3 is also A. You can see in the picture, the distance between 1 and 3 is A. Great. Okay, and then the last one, 4-1, has one extra little step we have to do. This is the distance between 4 and 1. We can call this like R41 if we want. That's a nice little notation we can maybe start using. That distance is not A. It's the hypotenuse of the triangle. If this side is A and this side is A, how do we figure out the distance of R41? It's going to be the square root of a squared plus a squared, which is going to equal the square root of 2a squared, which is going to equal a square root 2. Pythagorean's theorem. A squared plus b squared equals c squared. But we need to find it, so we did. So we have k, q1, q4 over r41 squared. The value of q1 is q. The value of q4 is negative q, but we take the absolute value. And then we're going to square this in the bottom. So we're going to square a square root 2. And so this just comes down to kq squared over 2a squared. Okay. The last step I'm going to leave for you all. It's literally just take these and put them in there. That's the last step. All you need to do is take these and put them in there. So, I'll even highlight which ones go where. 4-1, and I'm not going to have time in class to let you all do it, unfortunately. So, 4-1 goes where 4-1 is. 3-1 goes where 3-1 is. And then the last one, another color, green. Let's see if it's too bright in there. That's good. It goes here. And then I have my x component, and I have my y component. And if we go back to the answer is written actually already split up in the x and the y. Look, there's the x component. The I hat means X component. That's a physics 1 thing. And there's the Y component. I didn't combine them. I left the answers in vector notation. Meaning I didn't do Pythagoras theorem to recombine them together. You can do it if you want to. Great time, fun time, but this is sufficient for me. Direction, you will do tangent inverse of this over this. Direction, again, this is a vector. How do you find direction, tangent inverse of the Y component over the X component? So at this point, it is just math. The rest of it that's left is just math. The physics is done. The only physics we did was opposites attract and like charges repel, and the equation for the force. That was the only physics. Everything else was, and sum of forces. That's physics 1. That is physics. So that's it for this one. Again, I'll leave this kind of for you all to kind of finish it up. Make sure any problem I solve in class, even though it's from the problem sets, even though I've done it in class, you still want to try this yourself without the solution there. This is true of any of your classes. I was just meeting with a student yesterday. This is a great recommendation. If an instructor solves a problem in class, it's probably a good problem. That's generally a good rule of thumb for any of your future classes. Why did I pick these problems to do? Because they have a lot of skills and a lot of things going on in them that you all need to know. So, make sure you all try this without the solutions right in front of you. Do not just solve this by looking back and forth between my solutions and a blank piece of paper. Because what you're effectively doing is it's like reading a book and just having the book there and copying exactly what the book says. You're not reading, you're not understanding, you're just copying. There's not any learning happening there. So, these are all the problems, these are the strategies. So, finish this one up at some point, start from scratch, in fact. And then this one I'm going to kind of blaze through a little quickly, because it's going to be very similar skills. As weird as it sounds, there's just one extra thing you need to, it's basically the same exact skills, but in a different perspective. 2 balls are shown, they're hanging from some wires or something. They each have a mass of 0.2 grams. They're hanging from these wires that are 50 centimeters long, and they make an angle of 37 to the vertical. If the charges are the same, how large is each charge? So the question is, we always need to start with what are we solving for? In this one, we are solving for Q. The variable for charge is Q. I've only given you all 2 equations that have Q in it. So we're probably going to use one of them. The one of them I gave you was that net charge equaled number of protons minus number of electrons times 1.6 e to the minus 19. That's probably not going to be very useful for this problem. I didn't tell you anything about protons, anything about electrons, how many, so that's probably not going to be used. Okay, so what's the other equation? The force between 2 charges is given by K, Q1, Q2 over R squared. Okay, so that's an equation that has charge in it. What that then gives us a hint is that we should probably care about forces, which makes us think, why are these charges doing this? Why are these charges hanging like this, in static, in the air, just flying there? Because there's a force. There's an electric force on it. Now, the second you talk about forces, you should talk about every force acting on it. Anytime we care about one force, we generally care about all the forces going on. Why is this thing hanging like this? This is not the only force acting on it. If this was the only force acting on it, these things would fly away from each other forever and ever and ever and ever and ever. What is holding them there? So we do have the electric force acting on each of these. They have identical charges, which means they're going to repel, which is the only reason they would do this anyway. These are not the only forces acting on it. I will give you all like 30 seconds. See if you can come up with the other forces. Think about it. You don't like 30 others, just think about it. See if you can draw them, that kind of thing. In each one, there's 2 forces each one should have on them. 2 more forces, 3 total. All right. They're hanging down. Something must be pulling them down. Otherwise, why would they hang down? There's gravity. Each of these has gravity. They have mass, they're hanging down, something must be making them pull down. If there was no gravity, they would just fly off to the sides further. And there's a tension in this wire. So I drew it on both objects. We actually only care about one of them. Pick your favorite. Pick the left side, pick the right side. They're identical as far as we can say. So pick one of them. We're going to pick the left side because. So anytime we have this, a static situation, one of the things that's from physics 1 is that F net equals ma. Newton's second law, super, super important. In this specific problem, it's going to equal 0. It is not moving faster, it is not moving slower, it is not changing direction. They're just sitting there. So, what I can do is I can do this in the x and the y. In the x direction, and again, I'm going to move a little bit quicker here, and I'm going to write, because just for the sake of time. In this case, it's going to be ft in the x direction, and this is where I warned you all. In the x direction, it's going to be sine of 37. Why? Because this angle, if I want the x component of the tension, this is 37. In fact, I'll draw it up here just because I don't really have space here. So here's ft. If I draw a beautiful triangle, this is 37. The x component's opposite, so it's sine. This is why I warned you all that x components can be sine. It's positive because it's up. And then we're going to minus the electric force, Fe. Boom, that goes there. And all that equals 0. In the y direction, we're going to have ft times cosine of 37 for the same reasons before. And then we're going to minus fg equals 0. Now, you do need to remember that fg is m times g. You're going to have to plug that in. Fe is still going to equal kq1 q2 over r squared. Same old equation. The only extra thing, and I'll point this out here, and this is kind of where I'll leave it, r is not 50 centimeters. Draw R on your picture. This is R. R is the distance between the charges. What is this distance? We know this is 50 centimeters, so we can find half of R through some beautiful trigonometry. If we draw that right over here, we have this is 50 centimeters, this is 37, so therefore this is going to be, you know what? Let's make sure we write this in... Convert it sooner than later, you will forget. So this side's going to be 0.5 times sine of 37. That's how far. Now, that is not R, that is half of R. If you look at your picture, that's just half of it. How do you make it R? Double it. So, at this point then, it's just two equations. You know M, you know G. You don't know ft. You can solve for it with one of the equations, then you can plug it into the top one. There's a reason this is the last problem in this problem set. It's got a bunch of skills. You all need to be able to do this problem. Like, it's a useful problem. There's a lot of great skills here that you all need to know. You're going to be doing this stuff. Electrical engineers, system of equations are going to come up in some, with Kirchhoff's law in the future class. Mechanical and aerospace engineering, I don't know if aerospace takes statics. Maybe they don't. Mechanical and civics, whatever it is. Civil engineers, you are going to have to take statics, system of equations. You got to be used to building the equations, solving for them. Net force equals ma, and in this case equaling 0. That is the entirety of your all's statics course. The entirety of statics is net force equals 0 and net torque equals 0, and that's the entire class of solving problems. So, get used to doing these. They're important problems you all need to be able to do. Yeah? Yeah. So R is the distance between the two charges. So we have R here is the distance between charge 1 and charge 2. And then to get R, we look at our picture. We know that this string is 50 centimeters. So by turning it into a triangle, like we did here, we can find the length of this one side. And if we double that, so to kind of draw this maybe a little bit more explicitly, that purple and that purple are the same. So if I can find that side and I double it, it will give me R total. Yeah. I converted it to meters. You always want to convert your units to base units. One thing that many people will make a mistake on this problem. One last thing I'll mention. I give mass in grams. That is not the base unit. Grams is not the base unit for mass. The base unit is kilograms. M in this problem does not equal 0.2. It equals 0.0002 kilograms. You need to remember to convert your units. Grams is a classic one that's a pain in the butt. It is the only unit I'm aware of where the base unit has a prefix in front of it, has a kilo. Why? I don't know. The history. Take it up with them. I didn't decide these things. I just teach them to you. So, there you go. And this is, like, I just wrote the basics here. This is a problem that's going to, write it out. Give yourself space. One of my favorite things. I like working with a blank sheet of white paper. That's my preferred, but make sure you give yourself space. Multiple sheets of white paper or lined paper or do it on your computer. I don't really care. Do not cram it into a tight space. Because you need to read it later, probably. You probably should look at it at some point in the future. And, gosh, you'll learn. You'll learn that it's like, why did I do this? Did I cram this in here? On a test, I will give you all plenty of space to solve problems. I will give you all scratch paper. Generally, most people won't even need the scratch paper. On the test, I designed it to have space for problems for that exact reason. Just a very useful thing. All right, so those are those. Try them. They're good problems. There's a reason I kind of set them up. And again, do not look at this while you're solving it. Start from scratch. By the time the test comes, you need to be able to do these problems without a solution in front of you. By yourself, without someone else guiding you through it. That's one of the key ways of studying for any class. How do you know you're ready? When you can do it by yourself with only the materials that will be given on the test. So, it sounds obvious, and so the logic is kind of in itself. Okay, so now we're going to jump to electric fields. And Gauss's law, but I think I have I think I separated Gauss's law into its own PowerPoint slide. So, up to this point, we said like charges repel, opposites attract. Opposites attract, like charges repel. Coulomb did an experiment, came up with the equation that lets us calculate that force. Great stuff. What I'm going to be covering in this PowerPoint is one of the things that people were kind of iffy about is, so Coulomb charges, great, there's that one. What causes this force? That was kind of the next question. There is a force, but people didn't like this action at a distance. That's the phrase they use for it. Action means they were affecting each other even though they were not touching each other. And people were like, I don't like that. Everything I'm used to in life, how I move a table, I have to physically touch it. How do you basically have it? You have two things interacting, physically interacting. So how do they solve this problem? They made up something called the electric field. And this is what is quote-unquote touching another object. So basically this entire PowerPoint, a vast majority of it, is charges make a field and other charges experience that field. And it just explains the forces. But this field model is super useful mathematically, and it lets us solve problems and explain things. One of the things that's also really important about this field model is that information is not communicated instantly. So when one charge moves, the other charge doesn't know that charge moved at that exact moment. Case in point, if the sun blew up right now, you all would not know for 6 minutes. Why? Because the speed of light. There is a limit to which information can travel, and so this electric field is something that we kind of say is updates. It takes time for it to update, and that'll be relevant for us when we talk about making light and things like that. So anyway, that's a quick overview. We're going to talk about electric fields, electric flux. Everything here is just basically about electric field and how to calculate it. And the purpose of this is to explain why there's a force. Is the electric field real? It's a theory. It's one of those, I don't know, but it's useful. That's what it kind of comes down to. The force is definitely real. We know that two charges repel each other. Why they repel each other? We made up a thing called a field, and it's very useful. Is it real? Depends on what you define as real and things like that. We don't know. It's a theory. It's a theory to explain it, but it seems to be pretty good. So, this is the connect this to physics 1. If the Earth and Moon are not touching, how do they affect each other? What do you all think? This one I'll just kind of take guesses.
Gravity.
Gravity, great, okay. Gravity, that's it. What makes gravity happen? That's the next question.
I have no idea.
Mass makes gravity. But, what is gravity? There's a couple of specific theories that explain this. There's a couple of theories that explain this gravitational thing. Oh, okay, there is some idea that it's a particle. I guess that's a third wild card. But nevertheless, that's good. There's a theoretical particle like a graviton or something.
Like hills and caverns.
So there's hills and caverns that cause it. Yes, so there's two theories. The old one was fields, gravitational fields. Everything makes a gravitational field. So like if I drew the Earth, so this is the quote-unquote old model. There's the Earth, and it makes a field. This is a vector field. It is something that has a direction and a magnitude. So it makes a field everywhere. Here's my beautiful field. Notice that it gets weaker and weaker as I get farther and farther away, because gravity gets weaker and weaker the farther and farther away. This field exists even if nothing else is in it. So this Earth makes a field everywhere. This field is doing nothing. It's just existing. When does it do something? When I put another object with mass in that field, it doesn't care that this exists. It sees the field, and it therefore experiences a force due to the field. It doesn't need to know the Earth exists. It just is in this field. This causes the field. This experiences the field and experiences a force through the field. This is the idea of a field. It makes this field everywhere. When you put something in that field, regardless of kind of where you put it, if it's in that field, it experiences a force. You don't need to know what object is causing it. You just need to know the value of the field at that point. If you know the value of the field, you just multiply it by the mass of the object, and boom, you got the force. That's the idea. And this explains action at a distance. The moon is not touching the Earth, but it is touching the field made by the Earth. That's the idea. There's a field at this point, it quote-unquote is touching that field, experiencing that field at that point. And when the Earth moves, this field does not update instantaneously. This field would update, it would take the speed of light. It takes time for this field to realize to change. Nothing travels faster than the speed of light that we are aware of. So great, that's the idea of a field. Any force we talk about is caused by fields, at least for the purpose of this class. Gravitational force, gravitational fields. Electric force, electric fields. It helps us explain this object at a distance. One object makes a field, the other experiences a field. And the reason we call it a field, I don't know, I'm just making this up. I honestly don't know, but it makes sense to me. It's like a field, it's like a spread out thing. Like a field of grain is spread out, and at various points, there's different vectors. We call it generally like a vector field. Field because it's just spread out everywhere. Vectors because they're arrows. Vector field sounds really fancy, but it's just a bunch of vectors spread out over space. Where they, as you get farther, they tend to get weaker. Okay, so fields. One thing I didn't mention in the last slide, remember I told you all that we're constantly updating our knowledge? Previously we thought gravitational fields explained things, and then, Einstein came along and he introduced special relativity, general relativity, where instead of it being fields, it's curved space-time, and it explains black holes, and great. We're not going to talk about it in this class, but I just want to remind you all, I'm teaching you all things that have been proven, quote-unquote, not fully correct. Let's maybe phrase it in that way. Fields are still useful, but there's we've discovered more accurate ways, but they're way too complicated, and what I'm going to teach you all is good enough for 99.9% of things. We're not getting near black holes, so we don't have to suffer the problems that come from fields around those. Alright, so, Faraday decided to come up with fields. He has this quote, which I kind of like. Again, I told you all, people didn't like this idea of action at distance. He said, I cannot conceive of curved lines of force without the condition of a physical existence in that intermediate space. It sounds real flowery language and things like that. Basically saying, I'm not cool with force without something like physically touching. That's basically the idea here. I got two objects that are affecting each other, they're not touching. I'm not cool with that. I need something, quote unquote, physically there where the other object is. So he introduced the idea of a field. He's like, hey, object makes a field, that's what's the physical thing that's making it happen. Just fun fact about him that always gets mentioned with him. I don't know too much of the details, but I've heard this a million times from people. Really, really good at doing experiments, but actually bad at math. So in physics, you have experimentalists and you have theorists, and both are really, really important. Experimentalists do exactly what you think they're going to do. They're doing experiments. Theorists come up with the rationales to either predict what's going to happen in that experiment, or, on the other side, to explain what the person discovered. Both are really important. Theorists come up with a prediction, experimentalists prove it. Experimentalists discover something new, they need theorists to explain why it is. Both are really, really important in the field of physics. You'll hear kind of both experimental physicists, or movies, they'll say, he's a theoretical physicist. That just means they're the person that do a lot of the math and the simulations. And I say math, a lot of theory people nowadays, it's computational work. They're coming up with these equations and things like that. These equations cannot be solved by hand. They have to be solved by a computer numerically. There are certain integrals that you all cannot come up with. It's called analytical solutions for. You have to do numerically with a computer. Fun fact, do with it what you make. All right. So, fields. This whole thing's on fields. If I can get you to be okay with this idea of what a field is, I've done a good job. A field is the alteration of space around a particle. What does that mean? It means when you put something there, it experiences a force. What is it doing to the space? That's a complex, I don't know. But when you put something there, it experiences a force. And all charges make an electric field around them. All masses make a gravitational field around them. And when you put something at that point, whatever the net field is, in the case of gravity, things will move in the direction of the field. In the case of electric fields, positive charges will move in the direction of the field. Negative charges will move the other way. That's how we know positives and negatives exist. They do opposite. Whatever a positive charge will do, a negative charge will always do the opposite. That's a good rule of thumb in this class. So, pretty much most things are defined by positive. They result in forces. I mentioned all this. Are they actually real? Who knows? But they're super useful. In fact, in later classes, we pretty much just always calculate the electric field. We don't worry about, we don't do Coulomb's law a bunch. We calculate the electric field, and then if you want the force, you just multiply it by a charge. That's all you do. So it's a pretty quick, simple step. Fields, yay, there they are.
That one.
Yeah, great. All right, so here's how it's defined. Here's how we define the field. Find the force that a positive charge would make, that a positive charge would experience, divided by that charge, and that's the field. That's it. So, whatever force a charge experiences, divide it by how much charge that charge has, and you get the electric field. You get what's causing the field. And the definition of the word is the force per unit charge, a small positive charge would field, you put it there. You make Q1, positive 1, then F equals E. That's the idea here. If you put a positive charge that has a value of 1, the force divided by 1 equals E. If the charge is something else, then you have to do the math. And the idea here, and this is the really, really, really important thing. In fact, I'm going to put some subscripts here to kind of help us with this. I got two charges here. Charge 1 and charge 2. I'm going to look at it one way. You can look at it both ways, but we're going to look at it one way. If I want the electric field at this point where charge 2 is located, if I wanted to find the electric field at the place where charge 2 is located, the electric field is charge 1, E1, 1 for charge 1, I would take the force experienced 1 on 2, the force that charge 1 makes on charge 2, and I divide it by charge 2. So the idea here, charge 2 experiences a force. Divide it by the magnitude of its charge, and you get the field that it's in. We don't care what's causing the field. You don't need to know what's causing the field. If you know the force on that charge, and you know the amount of that charge, divide those two things, and it gives you the field at that point. Put anything you want there, and it will experience that field. So that's the idea there. One charge makes a field, the other charge experiences a field. And it goes both ways. You could do the opposite. If I write this another way, I could do it right over here. If I want the field due to charge 2, where charge 1 is located, let's call this E2 equals question mark. On the other side, let's call this E1 equals question mark. If I wanted the value of the field due to charge 2, I'm still going to have the force. Instead of this, I'm going to do 2 on 1. It's the exact same thing. And I'm going to divide it by charge 1. Charge 1, in the first case, charge 1 makes the field. Charge 2 experiences the field. In the second case, charge 2 makes the field. Charge 1 experiences the field. This is always happening, The Earth makes a gravitational field. The Moon experiences a gravitational field. The Moon makes a gravitational field. The Earth experiences that gravitational field. Everything is making a field. Everything else experiences said field. So like all around you right now, there is a quote-unquote electric field that we could hypothetically measure. And if you put a charge there, it would move. A positive charge would move in the direction of that field. A negative charge would move opposite the direction of that field. If you know the field, you can predict which way things are going to move, even if you don't know what's causing the field. We can't account for every single charge in this room. This is the benefit here. If I just measure the field here, then I can predict what's going to happen without knowing what's causing the field in the first place. That's the benefit. All right. And these fields, they point, to kind of draw this for you all, these fields point away from positive charges. So at this point, the field due to the positive charge would point away. The field due to the negative charge points towards. Opposites. Positives always do what you like them to do. They always do what you'd expect. So in this case, positive charges, the field points away. Negative charges, the field points towards. You can see that in the picture. Negative charges, the fields all point towards. Positive charges, they all point away. It's just how they're defined. I don't make the rules, I just teach them to you. Someone decided to make positives one way, so therefore negatives will be the exact opposite. That part at least is physics, or like experimentally. So, let's see if that made sense. Here's a negative charge. Here is a random point. There is nothing there. There is nothing there at this black dot. There are no charges there. My question is, what is the electric field at that dot? Due to, there's only one negative charge around it, so it's going to be due to that charge. If there's multiple charges, then we'd have to deal with that. But there isn't. There's just the one. So, at that black dot, what is the direction of the electric field? Is it answer A says down to the left, answer B says up to the left, answer C says up to the right, answer D says down to the right, and E says none of these? For instance, you could say there's no field at all if you wanted to. Chat with your neighbors. There's only one right answer. You disagree with your neighbor. One is wrong and both is wrong.
Oh, we all.
All right, give y'all like 20 more seconds. And 5, 4, 3, 2, 1. All you need to know to answer this question is you first ask yourself what's causing the field, and then you need to remember electric fields point away from positives and towards negatives. So if I want the field at this point, it points towards the negative, and it is a vector. It's a vector. That's why it points in a direction. It both has a strength and a direction, a magnitude and a direction. If we had multiple charges, we would find the field due to each one of them, and you just add up the vectors. That's just foreshadowing of the future. So, great. There is a field. There is no force here. There is no force at this point, because the only reason there'd be a force if there was something to actually experience a force. There is nothing here, so there is no force at that point, because For there to be a force, something has to be experiencing a force. There needs to be a charge there. But there's no charge, there's just a point. Yeah. Yeah, so you wouldn't be able to do Coulomb's law here. That's a great question. Could you do Coulomb's here? You would not be able to do Coulomb's law because Coulomb's law is for force. So Coulomb's law would give you the force if there was a charge here. But this is good foreshadowing. I told you all that E equals F over Q. So we can easily, and this is just a nice foreshadowing that's going to help us see this. If you all want to derive the equation for electric field, it's, just put a Q on the bottom. We make up a Q. We call it Q2. It cancels out the other one. And so the expression for the electric field is very similar to the one for force. It just has one charge. One charge makes the field. When you have two charges, if they're interacting, then they're going to experience forces due to each other. So yeah, I'm glad you asked that. That'll help me convey that later. All right, now let's see if this one makes sense. An electric field points to the right. What's causing this field? Who knows? Which way will a negative charge experience a force if placed in this field? There's a field to the right. I put a negative charge there. Which way will it, quote unquote, want to move? Will it move up, down, left, or right? Will it be pulled or pushed? Pull and push are two sides of the same coin. Will we get pushed up, push down, push left, push right?
So the negative charge. Yeah. Oi, oi, oi. And I'm like trying to write it down because I know.
All right, give you all about 20 more seconds. In 5, 4, 3, 2, 1. All right, so what we're going to do is we're going to draw this field. Pictures are useful. There's my electric field, and we're going to put a negative charge in this field. And the question is, which way will the force be? Now, I'm going to give you many ways to think about this. The first one I'm going to kind of tell you, this is just a helpful thing to have in your mind. Negative charges always do the opposite of what you quote-unquote would want them to do. Negative charges always do the opposite of what's intuitive. So, we're going to see that when we get to the answer. How am I going to convince you all what the answer is? I'm not just going to give you a rule. I'm going to use what you already know. How do I make this field? We can pretend that something is causing something is. We can pretend we can make up charges. How would I make this field that points to the right? I could put a positive charge here on the left. Electric fields point away from positive charges. If we do that, then you all can lean on what you already know. Opposites attract. So, this is going to get attracted this way. That's one way. In fact, you can do the other thing. What makes an electric field here? You can put a negative charge on the other side. Electric fields point towards negative charges. What are these two charges going to do? Repel. It all connects together. But again, a really useful thing to have in your mind, negative charges always do the opposite of what you would want them to do intuitively. That's going to be useful in this class. So there you go. Fields, weird things, but incredibly useful. This whole PowerPoint's on, and the rest of the class we're going to be using them. See you all on Friday. Yeah,